Okay, here we are again, video 11. It's Monday the 28th, and we're going to continue talking about vector spaces, and bases. So let's recall. We're going to work on R2 a bit here because it's easy to draw a picture. So in R2, the standard basis, standard normal basis, beta is E1 comma E2, which are the columns of the identity matrix. Okay. Now, just to sort of motivate this, bases impose a coordinate system on R2. So in particular, for this basis, right, in R2, if we look at the two vectors, there's E1, there's E2. And if you want to move around this coordinate system, you move in linear combinations of E1 and E2 because we've imposed this basis onto R2. So in particular, if say I wanted to get to the vector 1 comma 6, so we're going to let x be, those are supposed to be in black. So x is going to be the vector 1 comma 6. I'm going to go over this way. So x is going to be 1 times 1 0 plus 6 times 0 1. And so in this game of chess, really, it's saying move over 1 unit in this direction, the E1 direction, and then move up 6 units in the 0 1 direction. So 3 4 5, we'll put 6 right up here, right? So we go over this way 1 and up this way 6, and we get the vector 1 comma 6. Okay. But as we showed before, bases are not unique. And we know the dimension of the vector space in this example is 2, and that means there has to be 2 basis vectors. But any 2 linearly independent basis vectors in a vector space of dimension 2 are automatically a basis. So let's look at a different basis of R2. We're going to use the vectors 1 0 and 1 2. And sure enough, not much to show here. There are 2 vectors. One's not a linear combination of the other. That means they're linearly independent. And there's 2 of them, which is the dimension of the vector space. So that means they're a basis. So in particular, if I take this vector x that we're looking at, 1 6, I can write it as a linear combination of these 2 guys. And what I get is it's minus 2 times 1 0 plus 3 times 1 2. And that's not supposed to be division. That's 1 over 2, the vector. Let me check this, right? So minus 2 plus 3 is 1. 0 plus 6, yes. So now we've said, okay, now I can write this as these 2, as a linear combination of these 2 vectors. And the minus 2 and the minus 3 are unique, but the vectors themselves forming the basis are not. So, okay, this still imposes a coordinate system, only now it looks a little different, right? So basis vector 1 is B1 here. That's actually equal to E1, so I'm just going to put that guy here. Right, so there's B1. But our vector 2 is this guy, B2. But we're playing the same game. We're basically saying I can only move to the right and diagonally. And that's okay. We just keep doing this. Here goes another one. Like that. Like that. Another one. Like that. Right? And so, well, this is actually our graph paper, isn't it? This is the B1, B2 graph paper. And 2, 4, I wasn't going to do this, but now here I am doing it. If we're going to use this graph paper to get to 1, 6, this says start here, go over this way 2. That's -2 times 1, 0. And then up 3, so it goes 1, 2, 3, up here to 1, 6. And even though it puts it in the same spot, right? We're both at 1, 6 on these two. I get there with a different route. All right, so this is actually a pretty cool relationship, and one we're going to exploit considerably in the future. So, like most things, this leads to a theorem. So let beta be some basis for vector space V. Then, and there are lots of Greek here, symbols for every x in V. So for every x in V, there exists a unique C1 down to Cn. These are scalars, such that x equals C1 B1 plus ... Cn Bn. We've been saying this all semester. Okay. Now, here's this definition. The coordinates of x relative to the basis, I'm going to put that in parentheses or quotes, are the weights C1 down to Cn. Okay. So the coordinates of x relevant to the basis we're talking about are the weights, and so we write this as a vector in Rn. So this says x, the vector x with respect to the basis b equals C1 down to Cn, which is an element of Rn. Right? And this is the coordinate vector of x relative to b. So called coordinate vector of x relative to b. Okay. So going back to our example continued. If we use the second basis we had there, the non-standard one, 1, 0, 1, 2 with our cool graph paper, then the vector x, which is 1, 6, equals, where the hell is it? 2 and 3, 2 and -3, -2 and 3. -2 b1 plus 3 b2. So the coordinate vector relative to this basis is -2, 3. All right, well, how did we get that? Well, what we did is we took the basis vectors 1, 0, 1, 2, And we multiplied it by, let's do this, C1, oops, shit. Got to get this right here. So if you take these basis vectors, put them in the column, and then multiplied by C1 and C2, you want to get 1, 6, right? That's what we did. We solved this. So that says here's X. Here's X. Here's the guy we're looking for. And this is some matrix, which we're going to call P sub B. Okay. And I'm done with that. And this is a matrix equation. So it's P sub B times the coordinate change vector equals the vector in question. So P is a coordinate change matrix. And if we want to go the other way with it, using left multiplication, and that's important here, if you wanted to find X, you would take the inverse of P, multiplied on the left, because it's on the left here. Remember, multiplication is not commutative. Okay, well, that leads to another theorem. And this is the one we're going to use the most. Let B be a basis for V, okay, for any vector space V. Then the mapping X to its coordinate vector is a one-to-one and onto linear transformation which, by the way, is called an isomorphism. When it's one-to-one and onto, it's called an isomorphism. From V onto Rn. Okay. So what this does is it transforms our basis vectors for a random vector space V, not in Rn, and translates it to Rn. And then we have all the power of matrix algebra. So just like I've been saying forever and ever and ever, everything turns into a matrix, including my favorite vector space, Pn. Right? So, example. The standard basis for Pn is going to be 1 t squared down to Tn. This is the standard basis for Pn. And so the isomorphism defined takes a vector P, a polynomial, and maps it to P under this guy. And it takes Pn and maps it to R of n plus 1. Okay. All right, let's do an example. In P, where am I at? P2. And if you had this for the homework you just turned in, it would have made your life considerably easier. And so, like most things, we'll have it for the future. So we're gonna let P1 be the vector 1 plus 2t squared. P2 is the vector 4 plus t plus 5t squared. And P3 is the vector 3 plus 2t. Using this theorem, we're going to show P1 and P2 and P3 are linearly dependent in P2. And that'll also say that they're not a basis for P2. Okay. All right, so here's what we do. We take this mapping and we find the coordinate vector with respect to P1, which is 1, 0, 2. The coordinate vector with respect to B of P2 is 4, 1, 5. And then P3's coordinate vector is 3, 2, 0. So now we're looking at column vectors. We throw these three into a matrix. Compute the row reduced echelon form of A and get 1, 0, minus 5, 0, 1, 2, 0, 0, 0. One free variable tells you there's a linear dependence. And if you read this properly and fiddle around, you get that 3 plus 2t, which is the third column in this guy. Right? Because we know the two pivot columns here and here in the original matrix, A will give us a basis for the subspace, but not for P2. And the third one is always going to be a linear combination of the first two. So it's going to be minus 5 times the first vector plus 2 times the second vector. I always write this down and check it. So this is what? Minus 5. I do have an eraser. All right, so it's minus 5 minus 10t squared plus 8 plus 2t plus 10t squared, and sure enough, that's 3 plus 2t. So there you go. All right, first part of homework 6, section 4.4. There will be more in the next video. Problems 7, 14, 17, 32, and 36. And this is due next Monday, October, whatever it is. Okay, I'll see you Wednesday.